Among the tools you use, you may find one like this. The tip and the head of this chisel are badly worn, and this chisel isn't of much use to you in this condition. As a maintenance mechanic, you frequently see problems like this. A part or a tool will wear so badly that it's no longer serviceable. Now, you don't want to just throw it away, but the question is, what can you do to fix it? Well, in many cases, resurfacing can return the part to a condition as good as it was originally. Now, this chisel, for example, can be resurfaced by grinding the tip and the head until the original shape is restored. But grinding is only one way to resurface a part. In this program, we're going to discuss three of the most common resurfacing techniques. These are grinding, lapping, and honing. Now, each of these techniques requires the use of an abrasive to remove material. Abrasives are substances which wear away material by friction. Resurfacing techniques vary according to the shape of the abrasive, whether it's a solid wheel like this, or a paste. They depend on the size of the abrasive particles. These are coarse, as you can see, and these are very, very fine. And it also depends on the shape of the part being resurfaced. Now, some parts are flat, and others like this are irregular. Now, grinding can be used on both flat and irregular surfaces. In grinding, the abrasive material is bonded together in wheels of varying shapes, and the abrasive wheel is turned by a power driver. Because the wheels are power-driven, grinding removes material very quickly, and therefore one advantage of grinding is that it is fast. Now, this speed, however, can also be a disadvantage. Since one slip-up can cause removal of too much material, precision grinding requires a skilled operator. Lapping, which is the second of our resurfacing techniques, involves putting an abrasive paste between two surfaces and then rubbing the surfaces together. In most cases, one of the two surfaces will be a lapping plate or lapping tool, and the other will be the piece that needs refinishing. When the part that needs refinishing has a flat surface, like this feather valve, then the lapping plate provides a flat surface to which the part can conform. When the part to be refinished does not have a flat surface, like this valve seat, then we can use a lapping tool that conforms to the shape of the part. Abrasive paste called lapping compound is put on the tool, and then the tool and seat are rubbed together like this. When the seat has been lapped with a lapping tool, the seat and the disc must be lapped together. Now, this process is called grinding in, but don't let the word grinding fool you. Grinding in is a lapping technique, not a grinding technique. Lapping, which includes grinding in, is a very slow process, but one that's quite accurate, producing extremely smooth finishes. The third resurfacing technique, honing, uses abrasive stones. These stones are moved over the part surface in both a rotary and back and forth motion. It's this two-part motion that makes honing unique. Honing is a relatively quick and easy method for refinishing inside cylinders. Flat surfaces like this knife edge can be honed too, but in this case, a two-part motion can't be used. Instead, a single back and forth motion like this is used to put a good sharp edge on a knife. Now, each of the three resurfacing methods that we've mentioned, that's grinding, lapping, and honing, uses abrasives to remove material. Before we discuss each method separately, we need to know something about the different types of abrasives. Abrasives, we said, are substances which wear away material by friction. They're made of tiny, sharp particles called grit. Different refinishing jobs require different kinds of abrasives and different size grits. Abrasives come in many forms as well as grit sizes. The grit can be bonded to paper as it is here. It can be bonded to cloth. It can be bonded together in shapes of wheels or discs. It can even come in a loose form like this, or it can be suspended in a paste called a carrier. Now, two of the most common abrasives used in resurfacing are silicon carbide and aluminum oxide. You'll frequently use aluminum oxide wheels for grinding and silicon carbide paste for lapping. They're especially good for hardened steel or cast iron parts because their grit is hard and sharp. For super hard metals, you might use a diamond abrasive, and for real soft metals, your choice will probably be a fused alumina abrasive. For special applications, there are other abrasives available, and these are covered in your text. But the choice of an abrasive depends on more than just what it's made of. It also depends on the size of the grit. A coarse grit will remove material quickly, but it will leave a rough finish. A fine grit will remove material slowly and leave a smooth finish. Grit size is rated on a number scale. The higher the number, the finer the grit, and the lower the number, the coarser the grit. Most common abrasives are available in grits ranging from 10, which is a very coarse grit, up to 1,000, a microfine grit. The wheel on this surface grinder has a grit of 60. It's being used as the first rough step in refinishing an air compressor feather valve. The final refinishing of the feather valve requires a polished finish, and for this job, we're using a 400 grit. Some parts, like this mechanical seal, require a mirror finish. Here, a plate impregnated with a microfine grit is being used. Well, as you can see, there are a lot of choices to be made when you're selecting the right abrasive for the job. What form the abrasive will take, what the grit will be made of, what size the grit will be, and what kind of carrier, and the composition of the grit itself. Before we answer these questions, let's stop the tape and review the material we've covered so far. Read the text and answer the questions at the end of the segment. If you have any questions, discuss them with your instructor. In the last segment, we looked at some of the types of abrasives used in resurfacing. In this segment, we're going to focus on abrasives used specifically for grinding, and we'll see how to select a grinding wheel. Then, in the next segment, we'll demonstrate grinding techniques. Now, since grinding is done with a grinding wheel, the first step in any grinding job is to pick the proper wheel. Wheels vary according to their shape, according to the type of abrasive and bonding material they use, and according to the speed at which they are designed to turn. Now, here are three examples of wheel shapes. This is a straight wheel. The grinding surface is here. Never grind on this side. It could cause the wheel to shatter. On this flaring cup, the grinding surface is here. And with this grinding disc, the piece is ground against the outer edge of this surface, right out here. Now, there are more than a dozen different wheel designs. The one that you'll use will depend in a large part on the type of wheel the grinder will accept. Generally, when you replace a wheel on a grinder, you should replace it with one of the same design unless you've previously cleared a change with your supervisor. Now, once the wheel shape is decided, the next step is to determine the proper abrasive and bonding material. This decision is based on the type and hardness of the material you're going to grind, the smoothness of the finish desired, and the speed with which the material must be ground. Each grinding wheel has a standard code which identifies the abrasive type, size, and bonding material. On this wheel, the code looks like this: A24P5V. The code consists of 5 parts. The first part is designated by a letter, the second by a number, the third by a letter, and so forth. The manufacturer may complicate this identification code by adding additional numbers or letters to the front or the back. But these are manufacturer's identification symbols only, and they won't tell you anything about the wheel. The problem, though, is to figure out which numbers and letters are part of the identification code and which ones are the manufacturer's code. Now, fortunately, there is a way to find just the 5-part code which identifies the wheel. Look for the first letter, which is followed by a number. This letter will be the first part of the 5-part code. Now, in this example, the first letter that's followed by a number is the second A. So the first part of the code is the letter A. The letter A identifies the type of abrasive. A means the abrasive is aluminum oxide. If it were C, the abrasive would be silicon carbide. A list of letter codes and the abrasives they stand for is provided in your text. The second position, a number, designates the grit size. 24 is a coarse grit. For grinding wheels, the usual grit size ranges from 10 to 600. The third position identifies the grade. A grade is really a measure of the ability of the bond to hold the abrasive grains in place. It's designated by a letter, with A being the softest or least able to hold the grains in place, and Z the hardest or most able to hold the abrasive grains in place. P means this wheel has a medium structure. The fourth position identifies the density of the wheel. The numbers will run from 1 up to 15 or more. Low numbers mean there is a lot of abrasive material that is close together, while higher numbers mean that there's less abrasive material that is further apart. 5 means that the abrasive is fairly dense. The structure number is optional and is sometimes omitted. The fifth position designates the type of material used for holding the abrasive grains in place. V identifies a vitrified bond. This is a bond made of a glass-like material. Rubber and shellac are examples of other bonding materials. Your text will go into more detail on the way a wheel is identified, but let's look at one more code and review its parts. This one obviously has a manufacturer's code in addition to the identification code. So what's the first step? Right. Find the first letter that is followed by a number, and that would be this C. Remember, the T is a manufacturing symbol and doesn't concern us. C means the wheel is made from silicon carbide. Next is 163. This means the wheel grit size is 163. That would be a fairly fine rather than a coarse grit. And then there's the letter P. This means a wheel is a medium grade. Now after P should be another number to indicate the structure of the wheel. But remember, we said this part of the code was optional, and in this case, the structure number has not been included. The B is the last part of the 5-part code, and it means the wheel is held together with a resinoid bond. The 5 at the end is another manufacturer's symbol. When choosing a wheel, then, there are quite a few factors you must consider. In the last segment, we discussed the choices of abrasives and grit size in relation to the hardness and type of the material being ground and how smooth the final finish must be. But there are other considerations. When selecting bond material, for example, you must consider the durability of the bond under the exact grinding conditions. Vitrified bonds, for instance, are rigid and keep their strength under high temperatures as long as the wheel temperature is even. but they're subject to cracking under impact or where large temperature differentials occur. So vitrified wheels would not be suitable where pieces were fed rapidly. Rapid feed can cause the grinding surface to become much hotter than the rest of the wheel, resulting in a large temperature differential. Organic bonds, on the other hand, such as resin, rubber, and shellac, have better mechanical and thermal shock resistance, and they're less rigid. This slight flexibility generates smoother surface finishes, but this flexibility also generates more heat and can cause the workpiece to burn. Now, organic bonds also can begin to soften and deteriorate under exposure to grinding fluids. So the selection of the proper wheel can be a complicated process with no clear-cut ideal wheel for a given job. Your accumulated experience and that of your fellow mechanics will be one of your best guides. Now, once the shape, abrasive, and bond material have been selected, 2 final checks are necessary. Now, first, check the size of the hole of the wheel and check the maximum safe speed of the wheel. If the hole in the wheel is too small, the wheel won't fit on the grinder. If it's too large, the wheel will wobble and could easily become imbalanced and fly apart. Maximum safe speed should be printed on each wheel. Compare this speed with the speed of the grinder, usually printed on the nameplate. The maximum safe speed of the wheel must always be higher than the rated speed of the grinder. If the grinder turns faster than the maximum safe speed of the wheel could fly apart, causing serious injury and disability. For this reason, if you find a wheel that does not have a maximum safe speed on it, do not use it. And likewise, if you come across a wheel with no identification code, do not use it. You have no way of knowing what it's designed for and what it can and cannot do. Even if it looks and feels just like the wheel you've been using, don't use it. You're just inviting injury. Now, with that, we've covered a few of the considerations when selecting a grinding wheel. More information is provided in your text. Now is a good time to stop and review the material in your text. Before going on to the next segment, you should be able to explain what each part of a wheel's identification code means. In this segment, we're going to use this grinder to resurface a chisel. We'll also see how to dress a wheel and how to change a wheel. The mechanic has already checked to make sure that the wheel on this grinder is the proper one. His next step is to inspect the wheel for damage. He looks for cracks or uneven wear. These glazed spots were caused by someone who didn't select the right wheel for a job. The material that was ground was too soft and has clogged the abrasive. This can usually be taken care of by dressing the wheel. With your eyes protected, turn the grinder on and let it come up to full speed. We'll be using this dresser to dress and true the surface of the grinding wheel. This part here must be held against the tool rest. Set the dresser on the tool rest and bring it in firm contact with the wheel. Move the dresser back and forth across the wheel until the grinding surface is clean and is approximately square with the sides of the wheel. Dressing not only smooths the wheel's surface, but also trues the wheel so that it's a perfect circle. The dressed wheel should look like this. Notice all the glaze spots are gone. Okay, let's look at another situation you'll probably run into. You inspect a wheel and find that it's been chipped. Never use a wheel in this condition. It could fly apart, so always replace it. New wheels must be checked for internal cracks. They can only be found by ringing the wheel. Suspend the wheel by its center hole and then tap the wheel lightly with a wooden mallet or the handle of a screwdriver. Listen carefully each time you hit the wheel. each ring must sound the same. If there's a crack in the wheel, the ringing sound will be different where the crack exists. If this occurs, you must discard the wheel and get another one. A cracked wheel can easily fly apart, causing serious injury. Now, the important thing to remember when sounding a wheel is to always hit the wheel in about the same spot all around the wheel. Now, if the first time you hit the wheel, you hit it closer to the outer edge, like that, and the next time you hit it toward the center, like that, there will be a difference in sound. And the sound will be different even though the wheel is not cracked. Also, don't be confused by the fact that different types of wheels sound different. For instance, this wheel. Now, what's important is that all the rings around any one wheel do sound the same. After the wheel has been wrung and no cracks are found, lock out the breaker to the grinder so it can't be turned on while the wheel is being changed. The mechanic has gotten a helper and is ready to begin changing the wheel. The first step, obviously, is to remove the old wheel. Begin by loosening the tool rest so it can be moved out of the way. And this will provide enough room to pull out the old wheel. Next, both end covers around the grinding wheel must be removed. These are held with screws. When you've removed the screws, go ahead and take the end covers off. And with the end covers off, the helper can hold the nut at the far end of the shaft while the mechanic breaks the near side nut free. The threads may be either right or left-handed, so be sure you know which it is before you attempt to remove the nut. Remove the outer flange and check for signs of wear. Slip the wheel off and inspect the inner flange. The flanges should be flat, smooth, and even. And then check inside the hood. If any particles have collected, they should be removed. Scrape the inside of the hood thoroughly and remove as many of the particles as you can. And then wipe the inner flange and shaft. The new wheel can now be put on the shaft. If you've selected the right hole size, it should slip on easily with just a few thousandths inch clearance. Now go ahead and put the outer flange and the shaft nut back on. The blotter on the wheel keeps the flange from wearing. Knowing how much to tighten a nut is a little tricky. A correctly mounted wheel should be just tight enough to prevent wheel slippage, but not so tight that the wheel could be cracked. Again, this knowledge comes with experience. Okay, with the shaft nut tightened, replace the end covers and spin the wheel by hand a few times to make sure it spins freely and without wobbling. Then reset the breaker to the grinder. But before you grind anything on the machine, there's one more step. The tool rest must be adjusted. In order to keep the piece that you're grinding from catching in the space between the wheel and the tool rest, the clearance between the rest and the wheel should not be more than 1/8 of an inch. And when you do tighten the tool rest back up, be sure to tighten it snugly. You sure don't want it to slip while you're using it. Now you can turn the grinder on and wait for it to come up to speed. And remember, the grinding wheel's going to be spinning several thousand times a minute, so be sure to protect your eyes. With your goggles on and the machine up to speed, you're ready to begin. To grind the head of the chisel, rest the chisel flat against the tool rest while angling the head to obtain the proper bevel. And occasionally quench the piece in water to keep it cool. Finally, don't grind in just one place. Move the piece back and forth so you don't wear a groove in the wheel. Okay, while the mechanic finishes grinding the head of the chisel, let's look at the proper way to grind the blade. If the angle is not too steep, the tool rest can be moved so that the tool is held directly against it, like this. This is a good method to use when an accurate angle must be ground. Alternatively, the tool rest can be left at a 90-degree angle and the tool itself can be angled. But when doing this, it's very important to hold the tool firmly against the tool rest. If it's held too loosely, it can get snagged by the wheel and you can get hurt. In fact, anytime you use a grinder, you must pay careful attention to what you're doing. Any failure to observe safety procedures can result in serious injury. All right, now, turn off the tape, and while you're reviewing the material in the text, see how many safety practices you can list that apply to grinding operations. In this segment, we'll look at a few more grinding techniques. We'll see how several types of portable hand grinders can be used, and then we'll see two resurfacing techniques, grinding and lapping, used together to refinish a part. But first, let's take a look at portable hand grinders. We'll start by seeing how this grinder with a cone-shaped wheel is used. Now, if you ever have to change wheels on a hand grinder, as we do here, first, disconnect the power supply, in this case air. Then use a pair of wrenches to loosen the collet. The old grinding tool can be removed and the new one installed. Be sure it's installed all the way into the collet and then tighten the nuts. And reconnect the power supply. Next, make sure the part you're going to grind is held firmly in place. We're using a chain pipe vise. Keeping the part in place is extremely important. A loose piece could easily flop around and become a safety hazard. And safety goggles are a must. Also, gloves and long sleeves are helpful in keeping burrs out of your skin. With practice, you'll develop a feel for grinding with a hand grinder. One thing to keep in mind is which way the wheel rotates. This wheel has a tendency to ride up the pipe, so the mechanic has to steady it against this upward force. Now, let's look at a portable grinder with a straight wheel. Here the mechanic is grinding the outside of a pipe to remove any rust or scale that may have built up. He's doing this in preparation to welding a patch onto the pipe. Now, this same kind of grinder can also be used to bevel the edge of a pipe. The choice of a cone-shaped wheel or a straight wheel to bevel a pipe is a matter of personal preference. You'll have to try both of them to see which one you prefer. A portable hand grinder can also be used with a cut-off wheel. A cut-off wheel cuts only along its outer edge. Never try to grind on the side of one of these wheels. The wheel could fly apart, causing serious injury. These are just a few of the different ways portable hand grinders can be used. There'll be more examples in your text. But now, let's turn our attention to surface grinders. We're going to resurface a pair of feather valves from an air compressor. In order to get the required final finish, we'll first grind them and then lap them. Before the job is begun, the necessary tools must be gathered. For the lapping job, you'll need a lapping plate, lapping compound, rags, solvent, and a brush, and you'll need a dressing tool for the grinder. While some grinders are automatic, this reciprocating table surface grinder is manually operated. The work is held in place by this magnetic chuck. The control for the head, which moves the grinding wheel up and down, is located here. This hand wheel is the transverse control. It moves the table in and out. And this hand wheel is the longitudinal control. It moves the table back and forth. On this machine, the hand wheels have been locked to prevent unauthorized use. Before grinding the valves, the first step is to dress the wheel. Place the diamond dresser on the magnetic chuck and energize the magnet. Then turn the machine on. This is a wet grinder. It uses grinding fluid to cool and lubricate the work. With the machine on, make an initial pass across the full width of the grinding wheel. Then adjust the head height so the grinding wheel will again make contact with the dresser. Make several more passes, adjusting the head height as necessary until the wheel has been properly dressed. Then turn the machine off, wait for the wheel to stop, and remove the dresser. The feather valve can now be wiped off and put on the magnetic chuck. Be sure that the side to be ground is face up. The head will have to be adjusted so that the grinding wheel is just above but not touching the feather valve. Since the dresser was higher than the feather valve, the head will have to be lowered quite a bit. When you have the head in approximately the right position, turn the grinder on and continue to lower the grinding head while moving the table back and forth. Contact must be made between the wheel and the feather valve, but only enough to remove a small amount of metal. Then begin feeding the piece slowly under the wheel while at the same time moving the piece back and forth. On some machines, this is easy because the longitudinal and transverse feeds are automatic, but on this machine, the feeds are manual. So it will take some practice to coordinate both feeds at the same time. Continue feeding the table back and forth and across the valve until one complete pass is made. Both feather valves should be ground this way. Remember, we said that there are two steps involved in refinishing feather valves. First, a certain amount of metal must be removed in order to get rid of high spots. And second, the final finish needs to be made smooth and even. Eliminating high spots may require you to remove quite a lot of material. This is why surface grinding is necessary. It can remove a lot of material quickly, but it's almost impossible for grinding to give us the smooth finish we need. So we'll have to complete the job by using a different resurfacing technique. And that technique is lapping. We'll see how to lap a feather valve in the next segment. But for now, turn off the tape and review the material in this segment. In the last segment, we ground a feather valve to remove the high spots, but we said that the finish we got from grinding was too rough and that we'd have to lap the valve to get the final smooth finish necessary. In lapping, a paste called a lapping compound is put between the valve and a lapping plate. Now, the compound consists of an abrasive grit suspended in an oil or water carrier. And when the valve is rubbed across the plate, the lapping compound gradually wears away and refinishes the valve surface. Relatively little wear occurs on the plate because it's very, very hard. And when the piece that's being lapped is flat, like this feather valve, the process is called flat lapping. Well, let's see how the process works. Before beginning, clean the valve surface to remove any grinding chips that remain. Start with the coarser lapping compound, in this case about 120, and put a little on the valve. Later on, you'll use a finer grit, about 220, to finish the job. And then begin lapping. Use a figure-8 motion and use as much of the lapping plate as possible. Don't use just the center or one side. With experience, you'll be able to tell when the lapping compound wears out. The sound of the valve moving across the plate will change slightly, and the valve will move more smoothly. When this happens, you'll need to reapply lapping compound. But first, use a solvent and a brush to clean the valve surface. And then wipe it with a lint-free cloth. Do the same with the lapping plate. Now, reapply lapping compound and repeat the process until you get the desired finish. You begin lapping by using a coarse abrasive. The advantage of a coarse abrasive is that it removes material fairly quickly. The disadvantage is that it leaves a rough surface finish. So, when you've gotten the surface flat and true with a coarse grit, switch to progressively finer grits until the valve finish becomes as smooth as desired. Now, if the accuracy of the final finish is especially important, a technique called bluing can be used to reveal the exact areas of contact that the valve will make against a known flat surface. The surface must be absolutely clean so that the dirt does not prevent a good contact between the part and the plate. Using a good lint-free wiper, make sure that the plate is absolutely dry. Okay, in bluing, a Prussian blue dye is applied in a thin film to the surface plate, like so. This plate has an extremely flat surface and is used as a standard for measuring how true another surface is. When applying the blue dye, you'll find it's relatively thick, and will take a little time to spread it evenly across the plate. When you have as much on as you think you'll need, then take a clean, dry, lint-free wiper and wipe off the excess. And with the residue left on your fingers, you may want to reapply that to the plate. Then, you set the part that you want to check flat on the plate, give it about an 1/8 or 1/4 turn, and then lift it off. The Prussian blue will be transferred to the feather valve. And if the valve is perfectly flat, the blue will cover the valve surface evenly. But if the valve has any high spots, the blue will be distributed unevenly. Only those spots which touch the surface plate will pick up any dye. So if the part is not entirely covered with blue, the part is probably not flat. But to be sure, you should check the part at several different points on the plate. If the results are the same each time, then the part will need to be lapped some more until it is flat. If the results are not the same each time, the surface plate may be uneven. These plates can be damaged by improper handling or use, so they should be checked periodically. If you suspect the plate is uneven, see your supervisor. He'll be able to tell you what to do. Now, the part of the feather valve that we just lapped is a stationary sealing surface. Once it's installed in an air compressor, it doesn't move and nothing rubs against it. But sometimes you will be working with parts that do rub against one another. This mechanical seal face, for example, will rub against another part. Only by making this surface extremely smooth and flat can we keep friction to a minimum. and this requires more precise lapping with very fine grit. We'll demonstrate the special techniques for lapping a mechanical seal in a moment. But before we do, let's quickly review some of the important points to be followed in any lapping process. First, it's important that the part to be lapped is clean. Any particles not removed may scratch the surface. Begin lapping with a coarse grit to make the job faster, but switch to finer grits at the end so a smooth finish can be obtained. If you're using a lapping plate, make sure you use the whole plate. If you just lap in the center, you'll cause the plate to wear unevenly. Practice lapping until you get the right feel for when the lapping compound should be cleaned off and new compound applied. Okay, now let's see how to lap the metal face of a mechanical seal. This job involves using both free and impregnated abrasives. Free abrasives are loose abrasives like lapping compounds. Impregnated abrasives are abrasives that are embedded directly into a lapping plate. The part that's being lapped will play an important role in determining whether a free or impregnated abrasive is used. This carbon face from another mechanical seal could only be lapped with a fixed abrasive. If a loose abrasive were used, it would embed in the carbon, eventually scoring the seal face. The metal face of a mechanical seal, however, can be lapped with either a free or impregnated abrasive. Often a free abrasive is used first to remove any grooves in the seal face. Then impregnated abrasives are used to finish the job, and that's the process we're going to use. First, clean the lapping plate with a solvent and a rag. We're going to start with a coarse grit microdiamond lapping compound. The mechanical seal face that we're going to lap is made of stellite, an extremely hard material. It can't be lapped by ordinary abrasives. It's for this reason that we use diamond lapping compound. Put a little bit of the coarser diamond compound on a roller and spread it evenly on the lapping plate. You don't need a lot of compound, but you do want to spread it as evenly as you can. Before you begin lapping, check that no foreign matter is on the seal surface. As you lap, use a figure-8 motion that covers the entire surface of the lapping plate. You don't have to apply much pressure, but you do need to apply the pressure evenly. Since the seal surface is very hard, it may require considerable time to complete the lapping job. Occasionally, you'll have to stop, clean off the part, and check the progress. If a groove still remains, you'll have to continue lapping with the coarser grit. When the groove has been removed, clean the lapping plate with solvent. Then roll the finer grit evenly over the surface of the plate. Continue lapping the mechanical seal until the dull finish left by the coarser lapping compound is removed. The harder the surface being lapped, the longer it'll take. When you've gotten it as smooth as you can using the lapping plate, clean it thoroughly. The next step involves switching to a precise lapping machine. This machine has a rotating lapping plate with impregnated abrasives in it. Turn the machine on and apply oil to the rotating plate and move the seal back and forth across the plate. Continue lapping and periodically checking the seal until the next level of smoothness is obtained. This may take quite a while. Then another lapping plate must be used. This plate, which also has impregnated abrasives, is especially designed to help get the final finish required for mechanical seals. Again, an oil is applied and lapping is done just as it was done before. When you think you're finished, you'll have to test the seal for flatness. We need a very accurate measurement of flatness here, one far more precise than we could get with bluing. We can get this measurement, however, by using monochromatic light and a special optical lens. The seal is put face up on the plate. Then the optical lens that's provided with the machine is cleaned and is put on the top of the seal. A red arrow shows which side of the lens should be against the seal. The lens focuses the light so that visible light bands are formed on the surface of the seal. In this drawing, the lines represent the light bands. These light bands, which are focused on the seal by the lens, follow the shape of the seal surface. If the lines are straight, as they are here, then the seal surface must be flat. But if they're curved, then the seal surface must be curved also, and the seal will require further lapping. There are a lot of light patterns which may form, and these are covered in more detail in your text. So I think this is a good time to stop and review the material we've covered. When you've finished your review, you should know not only how to lap a part, you should also know how to tell if you lapped it properly. So far, we've discussed the lapping of flat parts. In this segment, we'll see how to lap curved surfaces. We'll lap a valve seat. Now, this is called matched piece lapping. Instead of a lapping plate, we'll use a lapping tool like this. Now, keep in mind, however, that if the damage to a valve is extensive, the seat may have to be machined before it's lapped. Here is a valve that's been cut away so the inside surfaces can be seen. As we open the valve, you can see the steam cut we have to remove. When the valve is open, begin disassembly by removing the nut holding the hand wheel in place. Remove the hand wheel. Next, loosen and remove the packing gland nuts and studs. Then, in order to take the stem out, you need to unscrew and remove the yoke bushing. Once it's loosened with a wrench, it can be backed off by hand. You may later be able to use this bushing as a guide for the lapping tool. Next, remove the split gland bushings if the valve you're working on has them. Back the yoke bushing completely off the valve stem and pull the stem out of the valve. If the packing is tight, it may have to be removed with a packing puller. To begin lapping, put lapping compound and a little oil on the lapping tool. Then insert the tool in the valve and install the appropriate yoke bushing. The hole in the yoke bushing must be large enough to allow the lapping tool to move freely, but at the same time tight enough to keep the lapping tool at a right angle to the seat. Tightening the bushing slightly will prevent it from backing out while you're lapping. Then put the handle through the stem of the lapping tool. Rotate the lapping tool back and forth. Lift it occasionally to allow the lapping compound to be redistributed on the valve seat. Continue rotating the lapping tool back and forth and occasionally lifting it up and down until you can no longer feel the cutting action of the lapping compound. When this happens, pull the lapping tool up and clean off the old compound. Apply new grinding compound and oil and continue lapping. This valve has a deep gouge in the seat. It'll require considerable lapping before the groove is removed. Now, while that job is being completed, we'll use this valve to demonstrate the next two steps, grinding in and bluing. In grinding in, the valve disc itself is used as a lapping tool. For the disc to rub against the seat, the disc must be kept from rotating around the stem. In some cases, a pin is inserted through the disc and the stem. In other cases, a pad may be put between the disc and the stem. Then when the disc is tightened against the pad, it won't be able to rotate around the stem. And then the disc is used just like the lapping tool. We apply the lapping compound, then drop it, rotate it a little bit, lift it up, rotate it a little bit more to make sure that we distribute the lapping compound, and continue our grinding in operation. Now, once the valve has been ground in, it must be checked by bluing. But first, we have to get rid of the lapping compound, so we'll clean that off with a little cleaner, making sure we clean not only the disc, but the valve seat as well. And then, as before, let's be sure to dry the disc and the valve seat. And now we're ready to apply the Prussian blue to the disc. And as before, thread it on. It'll go on rather thickly, and then we want to wipe it off just a little bit. And now we're ready to lower the disc onto the seat and turn it about a quarter of a turn. Then lift the disc straight up. A blue line will appear where the disc and the seat meet. This seat and disc fit together properly, and a blue line runs completely around the valve seat. If the seat and disc did not match properly, there would be a break in the blue line. The break would indicate where the seat and disc did not touch. Only when bluing results in a continuous line around the valve seat is the job complete. All right. Now, we've seen the three steps in lapping a valve. First, use a lapping tool to refinish the valve seat. Then, grind in the valve disc against the valve seat. And third, blue the valve seat. Let's stop now and review the techniques involved in a lapping of a valve. It may help you in your review to compare lapping a valve and lapping a mechanical seal. Identifying similarities and differences will help you better understand both lapping processes. In this segment, we'll see the last of our three resurfacing techniques, honing. Honing involves rubbing a stone in two directions at once against a metal surface. In this case, a drill turns the honing stones in a circle, while at the same time, the mechanic moves the stones back and forth as he refinishes an air compressor cylinder. Let's take a closer look at the honing tool being used here. It consists of honing stones, wiper blades, a pinion, a frame, and an attached drive shaft. To assemble the tool, the two stones are slid into holes on opposite sides of the frame. Then the wiper blades are put into the holes on the sides adjacent to the stones. There should be a stone, a wiper blade, another stone, and another wiper blade. Finally, the adjusting pinion is inserted. Now, if all the parts have been assembled properly, rotating the pinion will cause the stones and wiper blades to move in and out. In this way, the size of the honing tool can be adjusted. Okay, if possible, you'll want to hold the piece firmly in place. This compressor cylinder was small enough that it could be put in a vise. Lay a few rags to catch dirt, oil, and metal particles from the honing. Then take a piece of emery cloth and lightly sand the inside of the cylinder. This sanding will create particles that must be removed before honing begins. So when you finish with the emery cloth, wipe the inside of the cylinder with a rag. And now the honing tool has to be adjusted so that it fits snugly inside the compressor cylinder. The stones and wipers can be moved in or out by rotating the pinion. Adjust the tension so that the stones are tight against the cylinder wall. Then back off about a quarter of a turn until you can slide them back and forth inside the cylinder. Then put the honing tool in a drill, tighten the chuck, plug the drill in, and insert the honing tool into the cylinder. Put a few drops of honing oil on the cylinder wall, make a final adjustment to the honing tool, and then start the drill. Periodically, the tension on the honing tool will have to be readjusted. Remember, honing involves two motions. The drill motor moves the honing tool in a circular direction, and you move it back and forth. When you move the honing tool, though, be sure to move it the full length of the cylinder. This is necessary in order to hone the cylinder evenly. You can check whether the cylinder is even by using micrometers. Mic the inside diameter at the front and back at several points around the cylinder. If you compare the cylinder we've finished with the one that hasn't been done, you can get an idea of the value of refinishing. The honed cylinder looks like new. Of course, honing isn't the only technique that can make a part look like new. We've discussed two other methods, grinding and lapping. Used properly, these three methods will handle almost any resurfacing job. Study these methods and become familiar with the pros and cons of each resurfacing technique. Then, when a resurfacing job comes up, you'll be the one who knows what to do and how to do it. Okay, let's turn off the tape and review the material we've covered in this program.